Atomic Physics, Lecture 6, Accounting for Spin in Schrödinger Approximation, Degeneracy of Energy. Topic 1, Accounting for Spin in Schrödinger Approximation. Paragraph 1, Dependence of the electron state on spin. An electron has a spin, that is, its own angular momentum. The state of the electron depends not only on its distance from the nucleus and orbital momentum, but also on the spin. More precisely, on the direction of the spin, since the magnitude of the electron's spin is always the same and therefore cannot act as a variable. However, the Schrödinger equation does not include a spin variable. Therefore, the wave functions resulting from solving the Schrödinger equation does not reflect the spin dependence of the electron's state. Therefore, in order to take into account the presence of spin in the Schrödinger approximation, it is necessary to additionally introduce a factor into the wave function that depends on the direction of the spin. Paragraph 2. Spin direction. The magnitude of the electron spin is always equal to the same value, a half, and the spin vector can have two directions. The spin direction is described by its projection onto the selected coordinate axis. The spin projection can take two values, minus half and plus half. These two values correspond to two possible spin directions that are opposite of each other. The same axis onto which the orbital momentum is projected is chosen as the axis onto which the spin is projected. Therefore, the spin and orbital momentum of an electron can be either parallel or anti-parallel to each other. Different spin projection values are numbered using a magnetic spin quantum number or simply a spin quantum number. Like the spin projection itself, the number can only take two values, minus half and plus half. Note that although the state of the electron depends on the direction of the spin, that is, on the spin quantum number, the parameters of the electron orbitals and energy levels do not depend on the direction of the spin. Paragraph 3. Magnetic spin moment. Just as the presence of an orbital moment in an electron determines the presence of a magnetic orbital moment in it, spin determines the presence of a magnetic spin moment in an electron, or its own magnetic moment. The magnetic spin moment is proportional to the spin, and its projection is proportional to the projection of the spin. Consequently, the projection of the magnetic moment, just like the projection of the spin, can take on two values opposite in sign. And these values are numbered using the same quantum number, the spin quantum number. The proportionality coefficient between the spin and the electron's own magnetic moment is equal to the electron's form factor multiplied by the Bohr magneton. The electron form factor is approximately 2. Its exact value is 2.00232. And since the spin is equal to a half, then for the electron's own moment, it turns out that it is almost equal to the Bohr magneton. Therefore, the Bohr magneton is also called the elementary magnetic moment. Topic 2. Degeneracy of energy. Paragraph 1. Parameters describing the state of the electron. Let us summarize some results about the description of the state of the atomic electron. As discussed earlier, the wave function resulting from solving the Schrödinger equation contains three quantum numbers. To fully describe the state of the electron, one more quantum number must be added to these three numbers, the spin number. That is, the state of an electron in a hydrogen-like atom completely depends on four quantum numbers: principal, orbital, magnetic, and spin numbers. This corresponds to the fact that different states of an electron differ in its distance from the nucleus, orbital momentum, magnitude and direction, and spin direction. In this case, energy is determined by only one, the main quantum number, and the orbital parameters are determined by three of the four listed quantum numbers. Namely, the electron's orbital is given by the principal, orbital, and magnetic numbers. That is, the structure of the orbital depends only on the distance of the electron from the nucleus and on the orbital momentum, its magnitude and direction. Since the parameters of the orbital do not depend on the spin number, which can take two values, the same orbital corresponds to both values of this quantum number. Consequently, the same orbital corresponds to two different states of the electron, differing in the direction of their spins. Therefore, two electrons can be in the same orbital at the same time. Paragraph 2. Degeneracy of energy levels. Just as two electrons can occupy the same orbital at the same time, more than one electron can occupy the same energy level at the same time. This is due to the fact that energy, like the orbital, is not determined by all possible quantum numbers. In this regard, atomic energy levels are said to be degenerate. They are degenerate in the orbital momentum, in its magnitude and direction, and the spin direction. That is, there is degeneracy in orbital, magnetic, and spin quantum numbers. Paragraph 3. Multiplicity of degeneracy of energy levels. The multiplicity of degeneracy of energy levels is equal to the number of different states in which the energy has the same value. That is, the multiplicity of degeneracy is equal to the number of electrons that can simultaneously occupy the same energy level. Due to the Pauli exclusion, electrons located at the same energy level must differ in some other characteristics, namely orbital momentum and spin, since electrons have no other characteristics which they could differ. Since the number of possible values of these other characteristics is finite, by counting them, one can determine what is the maximum number of electrons that can be at a particular energy level. In other words, the multiplicity of degeneracy of an energy level is equal to the number of different values of orbital, magnetic, and spin quantum numbers for a given principal quantum number corresponding to the number of the energy level. Calculations show that the multiplicity of degeneracy of a given energy level is equal to 2 times the square of its principal quantum number. Thus, the multiplicity of degeneracy of an energy level is uniquely determined by its principal number. And the higher the number, the greater the multiplicity of degeneracy, which means the more electrons can be at that level. Thus, the maximum possible number of electrons at different energy levels is different and is equal to 2 times the square of the principal number corresponding to a particular energy level. From the above, it follows that the greater the energy, the greater the number of electrons that can simultaneously have it.